In our first video, remember that we focused on building a cooling solution utilizing a combined heat and power, also known as CHP generator, and an absorption chiller. In this video, I'll show you how to build an integrated solution with renewable energy technologies to further reduce carbon emissions. First, we need to understand how Xendee minimizes carbon emissions. Remember that the Xendee optimization engine always optimizes system design and operation based on an objective function. Xendee's optimization engine can directly minimize CO2 emissions by setting reduce CO2 as the objective function, similar to how it can optimize for cost. In this case, it minimizes CO2 emissions into and out of the system. This includes emissions from utility electricity purchases, PPA electricity purchases, and fuel burn to power on-site technologies. Let's revisit our data center model from our cooling video to see how we can minimize CO2 emissions this time. Remember that our data center has both an electricity load and a cooling load. Additionally, we have an existing electric chiller that currently meets the cooling demand. This electric chiller in the current base case is powered by electricity purchased from the utility. With this demand, it currently costs $25 million in utility charges. This includes both the electricity to serve the regular electric demand of the building and the demand of the electric chiller. Remember that in video 1, we considered two cases. Case 1 was installing only non-CHP gas generators to reduce cost, which saved costs by improving the electric efficiency of the data center. However, the scenario significantly increased the carbon emissions by 24%. In case 2, we considered installing both CHP generators and an absorption chiller to also enhance the cooling efficiency, which reduced the operational costs even more. It also reduced the carbon emissions significantly compared to the generator-only case. However, carbon emissions were still 8% higher than the baseline case with the low carbon utility electricity. Our data center is in California, where utility emissions are lower than the national average, making it difficult to further reduce CO2 emissions. In the model, I have added the same CHP generator and absorption chiller as we did in the previous video. Let's now also add some renewable distributed energy resources to our model. To supplement our electricity demand, let's also add solar PV. We don't know how much solar PV is optimal, so we set it to consider to let Xendee decide. It's important to note that this data center is limited in land availability because of its location. I used the Define Space tool to approximately draw a space on which solar PV can be installed, and this gives me an estimated available install space. In the Optimize window, we can select Reduce CO2 as our objective. When you select Reduce CO2, you will also see a premium cost factor input. The premium cost factor defines how much more we are willing to spend compared to the reference case in order to reduce emissions. I set a premium cost factor of 1.1 of the base case, so that means I'm willing to pay 10% more in annual costs compared to what I would normally pay to operate my existing data center. A quick optimization tells us that we can install solar PV, CHP generators, and absorption chiller capacity. This result still saves 33% in total system costs annually, but it also reduces about 15% of CO2 emissions. Please note that in this solution, Xendee does not hit the premium cost factor and manages to stay well below the premium costs. We also see that Xendee chose to install the maximum capacity of solar PV, and we used up all the available space possible. Let's take a look at our system's dispatch. In the daytime, we get lots of solar PV production. This offsets electricity purchases from the utility, which in turn decreases emissions from the utility. In the heating dispatch, we see that the absorption chiller uses waste heat from the CHP generator to cool the facility. This decreases electricity purchases for the electric chiller, which in turn decreases emissions from the utility. Let's run an optimization with only the solar PV and CHP generator to see how our metrics would change without the absorption chiller. Quick Xendee tip. Instead of deleting a technology you had already entered in your model, you can actually set a technology's decision to forced, but set the install unit to 0. This will leave the technology in your model, but it will exclude it from the optimization. And this is what I'm doing with the absorption chiller. A new optimization without the absorption chiller tells us that while only having the solar PV and generator still saves costs and reduces emissions, the savings are much better when there is an absorption chiller present to utilize the waste heat. Here's a table of all the runs that I did, and it clearly shows that the best solution for a data center in California is to utilize CHP, absorption chiller, and renewables, since this will reduce both the costs and CO2 emissions most effectively. As we can see, adding solar PV is a great way to reduce our site's CO2 emissions because it offsets utility electricity purchases. Additionally, part of the reduction can also be attributed to using the absorption chiller because it utilizes waste heat from the CHP generator to cool the facility instead of using the existing electric chillers. In this model, investing in solar, CHP, and absorption chiller allows us to achieve significant cost savings while also reducing the highest levels of CO2. So there we have it. What topics in designing microgrids do you want to see next?